start the recording. This will be on YouTube as well. So we have the whole history of them and everything. And I'm just going to start again, just a geometry container. So this just gets you into the geometry or SOP context. And then make a line and make our typical wrangle. So again, we're going to be going in, just using a single wrangle to do all of the animation and the motion and stuff like that procedurally. Or kind of analytically is another phrase that people use, which is basically like no other cache or history or whatever is managed or calculated. Each frame is calculated kind of on the fly or using these analytical equations. So the reason I usually start with the line, I just wanted to, this is going to be a bit of a repeating some of the other steps. If you looked at the file, you might see some similar behaviors of like some kind of bouncing or moving, kind of like we were doing last week. So it is a little bit of a recap, but we'll be introducing some new stuff as well. I just wanted to talk about why I was starting with a line and doing things this way. So if you make the float variable, you can put the y position attribute into it. And the reason I'm calling this u, and the reason I usually start with a line like this, is it's just a quick way. The y position or the height of the line is the same thing as the uv coordinate. So if you keep track of this, and then you can do like the x. I was also calling this, I think I just need to add some more points. So if we set the x to u, then you get the diagonal line, kind of like a graphing calculator and all of that stuff. So in my equations breakdown, I was calling this time. That's one way to refer to it. You could also think of it as like a UV coordinate. If you do a UV texture node, you set this to rows and columns and just move the attribute class to points. And then if you look at a spreadsheet, you'll see this is the same thing as the height, because we're starting with a line that's just going from 0 to 1 in the up direction. If you change the length, then you'll see that these attributes do become different, but it's just, the reason I do it is just because it's a quick way to get started and get a attribute or a variable that's changing over the duration of the line. So if you don't have that and you're just supplying like constant numbers, you're just not going to be able to control as much stuff. So I could move the x position, just this is kind of offsetting everything horizontally, but it's not changing over the length of the line or over each individual point. So it's not as interesting, or you don't have as much control over it. So I hope that makes a little bit of sense if people were confused why I was starting with a line and then like moving this height into an extra variable. It's just my quick way of getting started and kind of capturing that as a UV coordinate. So another thing you can do is if you use a resample, you can also get the curve U attribute. This way, you turn off maximum segment length, and is the same idea. Instead of calling it UV or U, they just call this curve U. So again, this is doing the same thing here. It's just before you modify the points or modify the attributes or anything like that, you just make a copy of the height. You call it U, and that's going to be your UV coordinate that you can then keep using to look up and make things that change over the duration of the line. So we set X so that it moves over based off of the length or the height of the line. And then if I wanted to, I could set the height just set this using our sine function. And we have the start of a sine wave. And again, if you remember this sine function, the input that this takes in is, instead of going from 0 to 1, it's looking for things that are in kind of curve coordinates, or like people refer to pi, the circumference, or the equation to get like the perimeter of a circle is like 2 pi r. So this is this similar idea. It's along that same thought process. So you can just multiply this by something approximate. So this gives you half of a cycle, half of a circle. And then if you multiply that again by 2, then you get back to kind of the starting point. So it makes one full wave. And if you want to, there's a little cheat that you can do to not have to remember pi or manage it that quickly, or just it's less cumbersome. If you just do $sign pi, this will evaluate to something similar or very close to pi. The way that works is if you go into the aliases and variables over here, Houdini has included certain things like the file path of your scene. You can see pi here is extended on quite a few digits. You could get things like the version that the version of Houdini that the file was saved with, the time, how long ago the file was saved. But then they've included the Eulers, E, and pi for kind of mathematical reasons or whatever like that. There's other ways too you could go about retrieving pi, but this is another kind of convenient thing that I'll do sometimes. And then just continuing on, so I'll just call this U coordinate. And we'll also keep going with file sync. So if you do !hip in the chat, you'll get instructions if you want to install shelf tools to refresh with this link, or you can just manage it manually by downloading these files from the chat. So the next thing we were doing was the slope line intercept, or y equals mx plus b. I don't remember if it's intercept or intersect. I guess it's kind of the same thing. So the idea with this is that, again, we'll start with a UV coordinate. So let's make U, just set it equal to the input height. I'm going to set X to U, and then Y, this will be mx plus b. So the m is, can't you just write pi with no $sign? I don't think that will work. I guess it works. I've never realized that they might have updated it, that it gets internally recognized as a built-in variable. I didn't know about that. That's pretty useful. Let me double check here. Yeah, it looks like it's moving over. Very cool. No more $signs. All right. So back to this. This is our slope line intercept. Could add a comment here. This is y equals mx plus b. And then if you want the comment in the network editor, you could kind of see it there, and it's a little bit handy. So the slope, maybe we want this slope to be 2. And then our x in this circumstance is the u coordinate. So we'll just multiply u by that, and then we'll add, so that's the offset, and that's where this will intersect the x-axis. And we could try 0.5. And looks like I've made a mistake. Double equal signs here. All right. It takes some practice, but yeah, the kind of human mistakes can be hard to catch. Sometimes you need a second pair of eyes, or just coming back to it. Like if you've made a kind of careless error or whatever, you'll get used to seeing it, and then someone else like skimming your code or just rewriting it or taking a break and then coming back, and you'll probably catch your error. If you're just getting started, it can be hard to pick those out super quickly. All right. So let me look around at this. So now this is intersecting at, should be 0.5 for the height. And if we want, we could make like the slope 0. You just have like a horizontal line, no incline, or 1 is like a 45-degree angle, and you can adjust it here. So this is doing a 2D equation. This is the slope line intercept. And you'd see like I don't have any negative numbers because my u, or my starting position, is just going from 0 to 1. If I did do a transform node here and then moved the geometry down from like 0.5, then you would see you get the kind of more typical graphing axis that's centered kind of at the origin. You could do the same thing in your code if you wanted to. I could do u minus equals 0.5. And then that's the same thing. The same idea is like using the transform SOP up here is just modifying the coordinates in the same way. So the idea behind all of those is like if you ever use the TI-83, it might be on a newer version if you're a young kid in school. But this is where I'm getting this idea from, or this is what I learned when I was doing these kind of equations. So they have the shortcut, the function key up here that's like y equals, and you would type in your equation. It could be a sine wave. It could just be just y equals mx plus b, or any of that stuff. So that's kind of the same idea, or that's what we're visualizing over here. So if we want to move into 3D space, we can do something that's like a 3D intersection point. So again, I'm just going to assign a u variable that we're going to take from the height of the line, or the y position. And then for a 3-dimensional coordinate, you just do this set function. There's 2 ways to do it. If you use the set function, let me just show you what's going on. You just supply 3 coordinates with commas. And then this will move all of the different components, x, y, and z, to these 3 numbers. You can also do it using the curly brackets, like this, the Egyptian brackets, and you'll get the same result. This is basically defining kind of a constant when you do it this way. The reason I don't use this that much, or a lot of people don't use it, is that you can't use variables, or you can't use numbers that vary within these curly brackets. So if I wanted to make like a sine wave for one of these, I like sine of u, it's going to yell at me. It's going to say, I don't know if it's being that clear, but the reason is basically you can't use functions, or you can't use varying numbers that are inside of the curly brackets. So that's why people, even if you're assigning a constant number, people will still generally use this. There isn't like a tremendous speed or performance impact. It's more of just like a habit or convenience. If I wanted to do sine of u, should see it. So now that x is doing like a pendulum, swinging back and forth. If you wanted to see it a little bit better, you could also put u into this direction. And then again, if we multiply this by pi, then we're starting to get our wiggly. I don't know if this function will work. I can't get all those characters correct. This is too advanced for me. All right. So this, what we're going to be doing here is like a 3-dimensional. I don't have Word on this computer. It's too advanced of a function. So 3-dimensional intersection. And what you can use this for is your 3D position that this line will intersect the axis or the plane with. So we'll say x coordinate will be 0.5, y or height is going to be 0, and so you're explaining now why you need to use set function instead of just, like, it won't work. I was just explaining for coding purposes why some people use these curly brackets to set a 3D coordinate or a 3D position, and some people use the set function. So these curly brackets will work as long as you're just making, as long as you just put numbers inside of it. But as soon as you go to use a function or something like that, the compiler won't let you do it. So I basically never use these curly brackets, and I was just explaining why I do things like that. So even though I'm making just a constant 3D coordinate, I'm still using this set function because that's just the style that I use to code things. That way, if I do want to go back and modulate it with a sine function or add other equations to it, I can that option is always open to me. Old school Jack, how's it going? Yeah, so this is the intersection point. We're basically moving this position or all of the points in the line to this coordinate. If we want it to be intersecting or pointing in this direction, we can multiply this coordinate by the u, or scale it along that direction. So then we're stretching things in this direction, if that makes sense. Sorry, Mr. John K3, I can't, I'm in the middle of this, I can't open these links right now. So I'm just going to get rid of this. And let me, I think I've done something wrong here. So I want to set this 3D okay, I think I'm back on track. So this is going to be the direction that things are going in, and then you can scale it to have the line intersecting along that direction, if that makes sense. So what this is basically doing is saying, without this, when you just are setting a 3D vector, you're saying move, set all of your position to these 3D coordinates. So it's kind of like just overwriting everything. You have another option of doing the plus equals, and that will, instead of overwriting or copying over everything, what this is doing is an offset, or like a translation. So instead of setting everything to the same value, what we're doing here is just offsetting or moving everything. So we have the starting line position and then the ending position. And this is like, if you ever like following a map or a compass, you like use your magnetic compass or whatever. This is doing a similar thing where you're saying like, go offset in the X direction, 0.25 units, and then offset in the Y direction, 5 units. So that's the difference, or that's why people would use an equal sign to set the value, or the addition to make an offset, or to move, or to translate the points. So if you multiply, you do, this will scale everything in that direction. It's starting to make sense. Hopefully I've kind of blundered a little bit of this, but I'm going to try to keep kind of plowing through things right now. Magnetic compass on iPhone. Yeah, I'm going real old school. It's like mixing up of these terms don't mean the same things anymore. Robotnik, how's it going? So another thing you can do, instead of just stretching the line from the origin to this point, we can make motion if we start to incorporate time. So I'll usually make a copy of the global attribute like this. And then if you multiply u by time like this, then over the length of the scene, you'll get the stretching line. FJ Sam, how's it going? So what we're doing here is over time stretching the line towards in this general direction. And the main reason I do this, to link it up inside of a variable, is that if I'm using time in a bunch of places in my code, if I just go up here and multiply this by 8, every instance that I'm calling this variable, or this copy of the time, it will get scaled or sped up by a factor of 8. So this is, again, just like coding kind of styles or best practices or whatever. In terms of managing variables, it just makes things a little bit easier to keep track of or to adjust. Then if you want to build things out with sliders or user parameters, it makes that step even easier as well. You don't have to track down a bunch of different locations that you're using, like this global variable, and modify each one with your scalar. All right. So now, instead of doing things like this, if we just do Seagull Rush, how's it going? If we just do time minus u, then you'd see what's happening here is we're offsetting over time. I think what I'm going to do is split this up a little bit. So let me punch that in, and then I can do p times equals. So just start again with time. So you can see what we're doing here is we're just taking all of the points in the line, setting them to this coordinate, and then saying over time, move in that direction. These vects are relaxing, hopefully. This is meant to be I don't know, somewhat gentle, hopefully a gentle way for people to get adopting more vex stuff in their workflows. So multiplying it by time moves your position in that direction. And then if you offset time by your UV coordinate, then you can see you're stretching the line along that direction. So if I do u times a very small number, then you get a very little line that's moving in that direction. So again, if we want to keep things somewhat cleanly named, I'll just call this line scale, and then I'll put this in there. So this green line, what it's saying is using uninitialized variable, and basically what happened was I never told the compiler, or I never defined what this variable should hold or what number to set it to. So I think it's just setting it under the hood or to 0, and it's just giving me a warning saying you never said what this number should be or what this variable should hold, so it's never been initialized or it's never been defined. So if I just move this or set this equal to 0.01, then it will be back to the number that I had put in there. So again, the reason to do this is if you just have the number inside of here like this, eventually it will get quite confusing why you're multiplying it by this little number or what this number is doing. So by setting it as a variable and then putting it in here, if you come back to the code or someone else is reading it, then they just have a better description of what this number is doing or why it's in there. So this is pretty cool. We're kind of shooting a projectile or sending our line in a direction. And we can adjust this if we want to. So if we want the line to be going more in this direction, it's kind of like we're firing a laser or something like that right now. We don't have a ton of control over this right now. We're just firing it in a certain direction, and it's just going in that direction for infinity or forever. So kind of hopefully get a sense of what I'm aiming for right now. So these little lines are just, you could think of them all like a bunch of little projectiles or lasers. But in this case, they're going the other way, or kind of backwards. So if we want to do that, we can just do negative time, I believe. And then we have things going backwards. But everything is starting at the origin, or people just refer to the center of your axis or the center of your scene, like 0, 0, 0 as the origin. So everything is starting right now at the origin, which isn't, unfortunately, what we want. So just rearrange this function a little bit. We want to start using parentheses here to ensure we're doing the proper order of operations. And we want to do everything is negative, or negate everything, or the final result of all these operations that we're doing. And then I want to do -1 minus u. And just need to close the parentheses or the order of operations. So now we have a little bit more control over when this line will pass through the origin or the intersection point. This -1, what I'm doing is offsetting time by 1. So to make things a little bit more clear, if I do it, whoops, let me just do things like this, I think. All right. So if we add 1, the line is starting already 1 second past its intersection point. If we do negative, then the line is firing and hitting or passing through this at 1 second, or 24 frames per second. So the 1 second duration, it's going to cross through the origin, or 0, 0, 0. And then that last negative is just to flip everything around one more time. So again, instead of something being fired in a certain direction, we're just flipping it around. So this is like you're shooting something in this direction, then you just add the negative, and then this is more like something falling, like a raindrop or something like that. So again, one step closer, a piece of the puzzle to get to the final result. So yeah, that's a little bit confusing here, but hopefully it's starting to make sense. So if we want to control things a little bit, the number of points will change the behavior of the vex function. No, so this is why I'm using, another reason why I'm using the length of the line. You could set u to your point number, pt num. Some people work that way, but the reason why I don't do it is because it will change the result of your vex function. La Galactique, thank you for the prime. Let's go. So, and then you could, some people will do this. This is a bit advanced. But if you take your point number and you scale it, or you divide it by your total number of points, -1, then you'll get the same, this u will be normalized between 0 and 1. So it will no longer change the result if you update your point number. So some people will work this way. If you don't know that your line is exactly 1 unit long in a certain direction, it's safer to use this. But for working quickly and just trying out ideas with a line, it's just less typing. It's a little bit easier to read, or quicker for, I don't know, maybe easier for people to understand, or it's just less typing in general. So that's why I'm doing it this way. So if we're going to start adding comments, this will just be our intersection direction. Then if you're thinking of this kind of like in a 3D world or something like that, this is kind of like your physics conditions or your forces. So if you change x to 0, then you just have something falling directly down. If I make this 2, then the speed will become quicker. So this is, instead of traveling 1 unit, this right here is my falling time. 1 minus means after 1 second, it's going to intersect or pass through the line, the origin. So the more that I scale this, the quicker it will have the illusion of falling. So if I go 24 seconds in, or 24 frames in, that's exactly when it will pass through the origin or intersect the plane. Bashir, thank you for the Twitch Prime Gaming. So that's the idea with this. This is kind of like your direction and speed, if that makes sense. CG Rockstar, how's it going? So if I do a value of 2, then you have more of a horizontal thing, but it will always be passing through the origin or the center of your world at this specific time, which is an offset of 1 second. So this is a pretty good way to get started. So I'm just going to keep going and trying to think. So we'll do the next step now, which will be the impact. Just call it a decision. If I forget how to type. All right. Is that it? Let me just call this, I'm just going to call this something different. Condition. So this will be, what I'm calling is the impact, or the moment that it crosses this plane or intersects things, will be the impact time. So just going to grab all this code here and use it again to kind of, this will be our starting code for this wrangle. And the way that we can define like an impact condition, or how we know when it's intersected the plane, is if we just look at our global time. So you can see here we're doing time -1. So when this time is longer or greater value than 1, we'll know that it's crossed through. So if I do time is greater than 1, this is the conditional statement. I think I used it last time, but I didn't really explain it in that much detail. Basically, this is like a test statement, and it's saying it will return either 0 or 1, whether this is true or false. So you could use it in a lot of different situations. It's very similar to kind of the group field up here. If this evaluates to 1, it's like a true condition. Old school video game coding. Yeah, I mean, these techniques is cool to play around with and stuff like that for learning purposes, but it's definitely used a lot for old movies, video games, even current day ones. Particle systems will have simple rules and stuff like that. The coding might be a little bit different. Like they use nodes. Houdini does the same thing, but conditionals like is still sometimes still referred to an if statement. So if you go to the VOP, do this if block. This is a similar idea. This is just their visual representation of it. And then if you want to do the comparison, this would be the same thing as like equal, less than, greater than, etc. So what we want to do is check when the time has exceeded 1. We could do if time is greater than 1. One thing you could do, like if you just want to debug stuff, sometimes as I'm typing or prototyping ideas, I'll do this. Like you'd say, just set p equal to 0, 5, 0. So if I just want to check if it's working, just turn on the point display. And it looks like it's working. What this is saying is, once the time has surpassed 1 second, overwrite the position, all of the point coordinates with 0, 5, 0. So that's what is happening right now. There's other ways you could debug this. Sometimes people will work with the color attribute at CD for Houdini. They call it that. It's like the color diffuse. So in this case, by default, it gets a value of 1, 1, 1, or white. And then what this is doing, instead of setting the coordinates or the position, it's now setting the color to 0, 5, 0, or just something that's really bright in the green component. So this is another way to debug visually or just to check your results. So what I want to do is, it's going to be very similar to what we were doing the first week. If you guys remember, we were doing, if we go back to these functions we have, I just set this to scroll through every frame. This switch node checks a different wrangled result. So if you remember, we were working with sine. Let me get it over here. Where did it go? The sine function, doing an absolute value to do bouncing or to fold it. Anything that was negative becomes positive. And then further adjusting it using this exponential decay function. So this is our bouncing code right here. If we wanted to, we could go in and copy paste this or reuse it that way. I'm just going to kind of type it through here to just keep explaining things. So if you want to add more lines after an if statement, you'll need to use these Egyptian brackets or the curly brackets. If you don't have them, it will only execute the first line. It doesn't pay attention to the indentation. It will only execute the next statement it encounters. So if you want it to execute a series of statements or a kind of a list of commands or a list of lines, then you'll need to use these brackets, is just to specify the branch or how much of the code to execute. So we'll start adding our sine bouncing stuff. Boom. So instead of just continuing down unmodified, what we can do is say the p.y, the y position. I'm just going to set this equal to, we'll go with a sine wave. We can do time. And let's just see what happens with that. Okay, so time, just instead of t. It's time. It's Houdini time. So there's a few issues here. One of them is that because our time has run for 1 second, this sine wave isn't starting at 0, so it's starting at 1. So if we look at our other function of just the sine wave, we look at, just going to the front view. So as your time runs on, your output value from the sine function will change. So instead of setting this to just time, if we do time minus 1, then the sine function is basically starting at the start of the wave, instead of, without this offset, the sine function is snapping back to somewhere like close to the peak of it. So you see, it's like starting halfway through. So we subtract 1 here just to say, go back to the start of the sine wave. Then the next thing we want to do, let's just do first things first. I'm just going to set all of p to 0 to overwrite it. And then here we'll just look at the bouncing of things. So it's just so I don't have to keep moving the screen over and over again or whatever. Could also maybe just do p.x. I guess that's not really going to be too different. So just for right now, I'm just going to set the p, move everything, snap it to 0, and then we'll finish up this bouncing. So absolute, just to make sure anything that was below the origin is now above it. And then we're going to just add our exponential decay. So just using the classic 1 divided by the exponent of time. And I think we're good. We also want to make sure we're doing the similar offset of 1 second to make sure we're starting at the start of our decay function. So again, if we go over here, this was the decay. So if you're starting, I just want to be starting at the top of it, so that's why I offset time to get back to 0. If you start halfway through, it's just a little less predictable, as to you're already starting like a little bit damped. So just go back to this. So another reason, if we go look at the first bounce, if I do pull up my spreadsheet, if you're starting to additionally like modulate how high you want your first bounce to be, you just want to make sure that you're using a predictable value, or you're not starting like too far into this exponential function. All right. Then if you want your time or your bouncing or anything like that to speed up, you could modulate these other functions. So for example, if I wanted this bouncing behavior to speed up, just doing parentheses there for order of operations, if you multiply that like by 8, then your bouncing be 8 times as fast. The same idea over here, if you want to modify this decay equation, again, just put this in parentheses for order of operations, and then if I multiply that by 8, then my decay process is happening like 8 times as quick. get rid of these extra parentheses for right now. I think we're good. Put this back. All right. So we have our part of our raindrop stuff happening, but it's not dispersing, or it's not like spreading out properly. So there's another really interesting thing we can do using these sine functions. So if we, right now we're kind of defining, I was calling this earlier like a pendulum swinging. So let me just set this to u, and then, or I'm sorry, to 0. And then if I set this right here to time, over time this is swinging up and down. I'm just going to switch this maybe to x for right now and set this one to y. So left to right. If I turn on my stopwatch thing, you can see this is kind of like a clock swinging back and forth. Or if we look at it from this direction or the side angle, this could be someone running in a circle or going back and forth. So in just one dimension is just a point going from left to right, but it could be you're looking at someone running around in a circle or doing loops or something like that. So if we want to actually make this doing a circle or doing loops, we can use Pong game incoming. We can use, I'm going to do the z axis in this case. So that's going to be this direction. And then there's something that's kind of like a twin of the sine function. It's the cosine function. The way that works is it just is kind of starting half a cycle later. So if I just put in the same numbers, then we can see that this is actually running in a circle. So in this x direction, it's still doing the same thing. If we completely get it like flattened out, just going back and forth. But then in the other direction, it's doing the same thing but offset. So it's kind of like a cousin or like an evil twin or something like that, yeah. You don't necessarily need to use it if you wanted to just offset things manually using pi. I think you can, you'd need to do half pi. It's pi divided by 2. So cosine is the same thing as you're just offsetting by half of pi. But for like naming conventions and purposes like that, people use cosine just so it's a little bit more clear as to what they're doing. So I'll just say this is like move in circle, sine cos. And then this one, I'll try to explain it a little bit better. So the height, we'll set that to the sine of our UV coordinate. And again, we just want to scale that by pi to get like a better control over how many repetitions we're doing. And to see it, I'm just going to stretch the x, stretch it along the x-axis by its u coordinate. So before I did that, it was just all stacked up on itself like that. And then as this, whoops. So we do u, if I just multiply this by like a really small number, it's just stretched out a little bit. So if I just multiply it by u by the full amount, we fully stretch this out. If I want to keep doing more of the wavelengths, more repetitions, you just keep multiplying this. So you do 2 pi, and that will be one complete revolution. or 1 to get back to where it started from. So this, we'll just do sine wave. And then this one, we'll just use it to make a cosine. Yeah, that's another way to explain it. I mean, it's very, I don't know, kind of philosophy. It's more of like philosophy or something at a certain point. It depends how you're thinking about it. So this is cosine, and you can see now the differences of the two of them, if that makes sense. Is just offset. You could think about it by going from 0.5 to 0.5 or -1 and 1. One of the ways that I don't know what the best way is to not really set up to visualize it right now, but if you just have a circle, and I might be able to kind of do this. So this is the circle. Instead of doing this with Z, I'm going to do it with Y. So this follows the circle perfectly. If we just look at, we don't update Y, we just update only X. This is kind of following one dimension of the circle. And then if we do the same thing and update Y but not X, this is following the other coordinate of the system. So this is a more advanced technique of kind of switching coordinate spaces, but sine and cosine are kind of like the X and Y coordinates of the edge of a circle. So this is the more like textbook way to think about it or whatever. If you just look at unit circles, you might find other kind of animations or stuff of it. This one is kind of it unrolling and stuff here. So this is a better animation of what I was doing. So this sine and cosine are both giving you one-dimensional values, like just single digits or single coordinates, like X and Y. But then when you put them together and use one for X and one for Y, then you get a circular result, if that makes sense. This is all just like conceptual and very philosophical kind of. It's up to you how you want to think about it and how you want to use it. You can always use this like sine and manually offset everything by half pi. And you'll get the same result, but just the general practice and why people do it this way is because it's a little bit more clear. So again, there's kind of like just thinking of this as like retrieving circular coordinates. Much more profound. I mean, everyone learns differently. Everyone I kind of skipped textbooks and I was just eventually like reading code. I didn't do a ton of like college level math classes or anything like that. So I didn't have a very good understanding of it. And then eventually like this kind of more visual way of thinking about it or whatever kind of stuck for me. So yeah, it's like if you just go to a polygon, if you actually scale this circle down in different directions, so this is like slid down like this. If you imagine something going around the edge of a circle, but you're just looking at it in one dimension, this is like the result of a sine. And then when you combine both directions, you get the circle. So this, you can make it three-dimensional. You need some more equations and stuff like that to do it. I'll probably get into that kind of stuff in later streams. So this is basically, when you're doing it in 3 dimensions, that's what's called polar coordinates or spherical coordinates. like the UV texture for texture projections and stuff that can use polar coordinates. It's also like if you're ever looked at like a globe or like the Earth, you have latitude and longitude. So those lines are kind of like very similar to sine and cosine. You're using two numbers, the latitude and longitude, to define like a location on a 3D surface or on a circle. But yeah, again, this is this is getting on too much of a tangent for today's task. So I'll just leave this stuff over here if you want to keep playing around with it. Just call this sine cosine path. I'll just get rid of that. And then I'll update you guys with the file. I think I've done a bit of programming if you want to get back up to date with things. So we can use this. This is getting back to everything. This is why I got into this. This is why I went down that path. So if we want to spread things out circularly or radially, this is why we use the sine and cosine function like that. So let me get rid of this p.y for a second. And this is just, now it's 0. So if we do a set function here, we can do kind of our circular coordinates. So if I say the x of this set function is going to be a sine, in this case we can use the u coordinate because that's our uv coordinate, or just a number that goes from 0 to 1 over the length of the line, or our input geometry. And then we want to multiply that by pi and by 2 to scale it to fit the circle like we were doing in the earlier examples. And then for y, we'll just leave it at 0. And for z, we can use the cousin, the twin, the evil twin, the bizarro world universe. It's like the mirror, it's like another dimension. We'll do cosine. So let's see if it's, all right, so it's working. As soon as this intersects, as soon as the time reaches a limit, we're overwriting the position to be this circle. And then if you are just curious about this, numbers of scaling to 2 pi, if you just do half pi, or I'm sorry, just 1 pi, that's a semicircle or a half circle. So 2 pi is the complete circle. And then instead of just snapping or moving to a unit circle, what we can do is scale things out radially over time. So at the start here, we were talking about doing like 3-dimensional intersection, and to offset this line, I was just adding numbers to it. So if you want to scale anything in 3D around the origin, you can just do that using multiplication. So if we just look at the pig, they have this uniform slider here for scale. If you want to do that exact same process or concept, you can just take the position and multiply it by a number. So this is the same way to do a scale, but just looking at 3D coordinates. There's not a ton of good there's not a ton of good visual resources specific to Houdini that I know of. The CG Wiki, Matt Estella has a lot of good visual GIFs of different operations in Houdini. It's not specific to math. He does have a vex. If you go to his Joy of Vex page, he does go a little bit deeper into some math functions. You could also look up maybe the expression cookbook. I don't know how recent this is updated, but this is a somewhat good starting point. Some of these stuff, they do talk about the sine and cosine here. Some of the learning I did was with other programming languages. This is, I think they've updated it since I've been using it, but this is another pretty good visualization. When I was learning a lot of this stuff, I was using something called processing. And they have some visual examples and stuff of like math. So some of this stuff I learned and then transported the knowledge like into Vex my own way. But if you look around, you'd kind of put enough stuff together or whatever to hopefully have it make sense. But yeah, that's why I'm breaking everything down, trying to break everything down visually right now as well. Then with Vex or with these wrangles, you can do this CHF function. This is the channel float. So if I just call this scale, and then you click this drop down handle over here, this will create a slider. So what I've done here is this just is a more of a tool now, but again, it's just to show you guys that you're multiplying a number, multiply the position, the coordinates by a number, and you do a scale. If you do addition, then it's no longer doing a scale. It's kind of mislabeled, and it's doing an offset. It's just offsetting everything in the same direction because it's one number instead of three numbers. But for a scale, this is the uniform scale. So multiplies or scales everything using the same value. And then again, if you go negative, you get an inverted geometry, or sort of like reversed or flipped around. So scale with multiplication. The reason I'm explaining that is because we're going to use it to scale this circle now. So we can multiply this by time, and then over time our ripple with the circle is expanding. Again, you see we're running into the problem. This is why I was doing time -1 in the other places. So we just need to offset time. Basically, the value of time when this if statement is all executed will be 1, because it doesn't get executed until time is greater than 1. So if I do time -1, then we'll make sure that this starts at 0. So now it's a little bit closer to what we want. When it's hitting the ground, it's turning into a ripple or a growing circle. That's pretty cool. One thing we might want to do is keep this expansion going with our exponential decay. So you look at these functions, we have a breakdown or a bunch of other things we can do. Different ways to shape it. What we want to do is probably something like this. What I was using for friction to slow down the bouncing ball over time. We could use this again to slow down the ripple expansion over time. So I'm just looking at this and thinking we want something that gets larger, and then as time increases, the slope decreases, or the rate of change decreases. So thinking of this as time, this is our value. Over time, we just want it to slow down like that. So to do that, we can start with our basic exponential function, 1 divided by the exponent. But this is going the wrong way. So we wanted to just do our 1 minus. And then this is when things go wrong because we're not obeying the order of operations. So because I haven't specified with the parentheses right now, what's happening is this value, the multiplication is happening. So all this code is being executed, and then it's getting this decay function subtracted from it. So if I want to be a little bit more explicit with the order of operations, put parentheses around this, and then the expected thing is happening. So this is to make sure 1 minus our decay function, or just inverting it, flipping it around. We go over here. This is what that 1 minus is doing. Without the 1 minus and without this, then it's just going the other way. So I'm doing 1 minus to flip it around. So that's why we do it. And then the parentheses is to say, do all of these steps and get the result instead of before you do this multiplication. So the parentheses, the order of operations stuff is really important with programming, as with all math. Now we have our ripple, and it's deaccelerating over time with that exponent. And again, if you want to change the rate of decay or any of this stuff, you can keep multiplying or scaling these values. So this, you see I ramped it up 3 times faster, 6 times faster, to how quickly it finishes its decay process. Okay. So if we bring back our bouncing equation, then we kind of have like a splashing, like a crown splash or a ripple or something like that. So this is, you're kind of doing some cheats here, because you're not doing like an actual flip simulation with surface tension and all that business, but just visually you want like a little impact with the droplet hits the ground and splits into a bunch of smaller droplets. So that's what we're doing, kind of cheating it or faking it with this math. So I think there's a pain in the ass with flip. Yeah, it can be difficult, and then especially if you wanted, where did my window go? If you wanted a bunch of these things all happening at once, it's going to be really slow to do it. Because I set this up with math, as I'm able to make it loop or repeat seamlessly. With simulations, it's a lot more difficult to get like things to keep repeating, lining up perfectly or whatever. All right. Thought it would be harder, kind of understanding everything. Hopefully, yeah, this is kind of the idea, is like we're just moving along at building on previous concepts, and I'm just trying to introduce smaller steps each time now. But if you're missing stuff, I recommend either doing some research on your own with math or visualizations, or just rewatching some of the older stuff, or I think enough times, hopefully it will click. It depends how you learn, whether it's visually or using math equations or other things like that. Looking at a textbook is what I mean with like the Greek letters and everything. All right. Just how did you learn to become so good in Houdini? Just over time. So one thing I want is this bouncing behavior probably to be maybe a little bit sped up. So I can just multiply this time in this instance, or for this usage, I'm going to multiply it by 4. So then the bounce rate is a little bit quicker, but you can see it's the amplitude, or the amount of bounce, is too high now for the impact. So if I just multiply the final result of this, maybe by like 0.25, then everything's a little bit smaller or shorter. The other thing you might want to do is I don't think we've done it yet, but there's a vex function you can use to modify. You could add points to geometry. With vex, you can remove points from geometry. You can modify geometry like that. So we can use one of those functions, which is the remove prim. This will delete whatever primitive number you tell it to delete. So in this case, 0 is going to be just the input, or the current geometry. In this case, I can use the @primnum attribute, or it's kind of like a virtual attribute. It's just, if I go over here to the primitives tab, it's just the current primitive number, the line. And then the last, it's airing out right now, so there's one more argument that I need to give to it. The arguments is just these comma separated values for the function. It's kind of the same idea as like variables or parameters. So again, if you're getting familiar with coding or stuff like that, or you're coming from VOPs, you'd see the similar thing here. So arguments with a function is the same thing here with node inputs. Is the handle, the primitive number, and points. And points is saying, up here you can see it's a little bit more human readable. Remove points as well. So the programming is just more of like a minimal, less fluff kind of. So if I do and points, no, I don't want to remove the points as well. I just want to remove the line. Then you can see we're keeping the points, but removing the primitive. It's a little bit weird the way that this is running right now, but it's okay. Basically, all of these points are telling the program, or telling Houdini to remove the primitive that they belong to. So it's basically getting like however many points, like 12 or 24 requests to delete the same primitive. But it's okay. Vex is good enough that it doesn't cause any issues. Or sometimes with more advanced programming languages, you'll get like a unallocated memory or like weird errors like that. But Vex is a little bit gentler in terms of that stuff. So is it still making sense so far to everyone? Hopefully. The remove prim is basically saying remove the primitive or the line that this point or whichever point belongs to, or is the parent. Again, this way is good if you're getting started with programming or Houdini or stuff like that. You can see it comes with a little bit more descriptions. Can be easier to find the functions you're looking for because you have the tab menu and you can put down stuff. If you're ever really curious, you can right click on these things. If you do type properties and go over to code, then you can actually see the equivalent vex function that it's running. But for working quickly and making longer snippets of code, in terms of like reusability here, you could see if I was really working just on my own in a production setting, I could just be grabbing little snippets, copying them, pasting them. Mixing and matching is why I prefer to use Vex. And if you structure things and name things well, it will be pretty easy to understand. Yeah, with VOPs, when you build bigger tools and things like that, it can just become a bit too messy to go in and modify. It can get into a situation where you can make something that's even if you intend to set it up to be really readable, you can make something that can take someone else like an hour or a day or even longer than that to properly like dissect and tear apart. So Vex is just a little bit more of like a universally understood way to communicate what you're trying to achieve, as long as you keep things clean and name it properly and stuff. Yeah, I mean, VOPs, there's times and places for it. I still use both all the time. But for this, especially something like this effect that's going to take a lot of lines of code and nested functions and stuff like that, it doesn't lend itself to work that well with VOPs. Yeah, the VOP is very nice for doing traditional kind of like shader editing type of things, like doing textures, color corrections, noises, kind of compositing. But when you start to move beyond that and doing like really intense logic and maths and stuff like that, is, especially for me, it just becomes too much to manage with VOPs. I mean, you could see, if this is a bit beyond the scope of everything, but if I just make a pop network, if you go into the pop solver, if you're curious about like how they're integrating these forces, the developer was nice enough to rewrite like in pseudocode what they were trying to achieve. If I just make this full screen, like just visually trying to think of what these functions are, and then there's if statements with snippets and stuff running inside of it becomes very quickly. It's just like you need to get out a notepad and take a minute to pull that apart. So it can be you can get into a situation where it's just better to, especially for like a tool that's, you want it to be reusable and really readable and stuff like that. This is a better way to usually to accomplish that kind of stuff. All right. So we have it hitting. The green color is a bit weird now. It's like a radioactive raindrop or something like that. One of the things we can do is keep going with that exponential function. So here, just copy and pasting, like I was saying, is kind of makes things reusable. As soon as once you start to get comfortable with the programming and stuff, it becomes a lot easier to reuse portions of code than it does if it was VOPs and wired together. Is a lot more tedious to reconnect things and everything. So because I'm on the black background, it kind of has the illusion that the droplets are like shrinking or just fading out or whatever like that. So the other thing I might want to do with these points is they all look pretty uniform. They're all moving radially or like expanding at the same rate, and they're all bouncing the same heights. So what I can do at the end here is just multiply this by a random, generate a random number for each point number, for each point. So then it looks a little bit more interesting visually. It's like a little bit more natural. So a lot of programming or artistry of effects is just using code, using randomness and noises to break up things and stuff like that. Again, like if you're, depends how you're working, but if you want to start splitting things up, I was doing that earlier into multiple lines of code. Sometimes that's a good idea just to, again, keep things readable. So if I just do a line break here, what I can do is keep multiplying the Y position, multiply the existing, this times equals, again, is multiply the existing value by this number and then store the result of it. It's a shortcut of saying, I think I went over this last time, but it's a shortcut for doing this. So sometimes I'll do this, split things up into multiple lines. So each line is kind of like a thought process. So we could just say randomize the bounce height of every point. Keep going along the same thought process with this one here. How long will the stream be? Getting close to wrapping things up, maybe another 30 minutes or 20 minutes or so. And then here we'll just keep doing times equals. So this will just say reduce the maximum scale of the bounce height to 25%. So 0.25 is the same thing as 25%. So instead of here giving people a really long kind of equation or statement or whatever to look at, I'll just keep doing it with this one and say at p dot y times equals. This one will just say exponential decay rate of expansion. Yeah, of course. Thanks for subscribing. Thanks for all the questions and everything like that, following along. Catch you in the VOD. Catch you in the YouTube, the YouTubes. Yeah, so this, just kind of breaking this into step-by-step fashion is, you will thank me later, or my future self will thank me later. Yeah, thanks for lurking, Seagull Rush. So again, this would just say absolute of sine to, I don't know what to convey bouncing. I don't know if convey is the right word, just to represent or to make it look like something. We'll just say simulate. It's not proper like Houdini simulation, but it's a mathematical like simulation of a bounce. All right. And I think I messed this one up. This is not the expansion. This is just the height. Decay rate of bouncing. So this one up here, if I keep naming things properly, we're just cleaning things up. At P, this is our exponential decay rate of expansion. Visually, the exact same result, but if you look over here, our eyes just have to do less reading. Each step is a little bit self-explanatory, or just easier it's more digestible, I think. It's raining. It's raining Vex. It's raining programs. So this is just say fade the color out over time. Do it. Easy to follow for noobs. Yeah, I mean, it's easy to follow, and then especially too, like I was saying, it just becomes more useful for even yourself. It's not something you always want to do, because sometimes you're just in a hurry. As Houdini, in the end, is an art program. You're just trying to create an interesting picture in the shortest amount of time. So it depends whether you're like learning, documenting, or you're just really blowing quickly to just something that's disposable. So the more reusable you want something to be, the more you want to kind of take the time to organize and clean things up. The same thing with the node graph. It's the same concept or the same idea. If you're working quickly, you don't care like where your nodes are dropping or what they're named, but if you're making something that you're going to keep using in the future, you want to start naming everything. All right. So this is our impact condition. We'll just say single drop. So we'll go next step. I'm going to start accelerating, getting through the rest of this effect, hopefully pretty quickly. So let's go back into our files. Could see some other things here. One of the things here that I was looking at or ended up using was this frac. I'm sorry to do it, guys. I ended up fracking. So the fracking for this situation is the fractional result, or the decimal remainder of things. So if we look at this here, we can just get rid of this one. It's doing the same thing. Without doing this, you just have a line that's constantly increasing. Just needs fracking. We need jobs. So instead of what this is just giving you the fractional result of things. So if you're thinking about doing division or stuff like that, if you have, so we'll just return everything to the right of the decimal place is the fractional result. If we look again over here at the geometry spreadsheet, if we look at this y coordinates, they're all fractional results, or they're all less than 1. If I undo this and look at the results, just need to go over, you could see this is like 3.6. Just try to highlight that, see if this works. Okay, so it's basically you're discarding the whole number. These poor maths. I'm fracking the decimals. So what this frac is doing here is it just discards the integer or the whole number and returns the decimal result. So numerically, you see what's happening is it's just keeping everything to the right of the decimal. Visually, with this function, you can see what's happening is instead of getting the constant increase, every time it's kind of resetting its rate of increase from 0 or from the origin. So we can use that over here to do something special, something really cool. What we can do is take the time and we're going to frac the time. So when we do the fractional result of the time, we can end up doing with this is having the time kind of just repeating or cycling itself. So when I just do time equals the fractional result of time, instead of time going from like 0 to 3 seconds, it's just going from 0 to 1, and then it's starting again at 0, and it starts incrementing from there, if that makes sense. So you'd start to modify this, the loop duration. You scale it by 2, divide it by 2, and then after you've gotten the fractional result, you want to multiply it by 2 to scale it back to its original length or speed. So now what I'm doing here is basically looping 2 seconds of time. So visually, if we were to look at a graph of t or time, it would be the same zigzag of starting, repeating, starting, and repeating. So again, if I want to keep naming things nicely, this will be loop duration. And this is, again, because you don't want to keep typing like the same number. If I want to loop 3 seconds, I would have to keep going in and changing both of those numbers. So if I just set this loop duration to 2 seconds or to 2, then I can go in here and just have to update that one variable. It's a little bit more descriptive instead of just updating these random numbers that someone picking up the code, or they might not know that those two numbers have to be the same, or they don't know why you're using it or anything like that. You're fracking over there, Seagull Rush? Extracting these black dollars? All right. So that's what we can do with this. So we have our one droplet and it's doing what we want. Now we just need to quickly loop time with frac function. Mining. All right. So let's just do another share of the scene if anyone's fallen behind or they don't want to retype out stuff. What I'm going to do here is we'll start to be our final rain. And what I'm going to do here is just use a copy and transform node. This is just a quick way of duplicating or making copies of our line. So this is going to be the amount of droplets we want to create. You could do this kind of stuff in Vex, but it isn't that good at it. All the code it runs at multi-threads very well, except for doing geometry deletion and geometry creation. This remove, we kind of have to do it during the code because we're removing certain lines after condition and stuff like that. But if you want to generate a ton of lines, it's a lot easier or quicker for the computer to do it once and then run this code. And you can see that there's this clock here that means it depends on time. So every time or every instance where your scene time changes, this code has to be re-executed or rerun. If we just create a bunch of lines, that doesn't need to be updated. So it's a little bit optimized or better to do it this way. This is why I am doing the copy SOP. And then if I do a translation offset, you can see all of the copies that we're creating. I don't need to worry about that. So I'm just making a bunch of copies and they're all stacked up, still going from 0 to 1 for the UV coordinate. So when we play it, we have all of them. When the droplets explode or the droplet hits the ground, you can see that's where the randomness kicks in. So we're still, every point number is getting a random bounce height. We can just start to extend what we're doing with that randomness. So the very first thing we can do is do a time offset. Just do minus equals. And I'm going to offset the time with a random number, but I want to generate the random number based off of the primitive number instead of the point number. So as soon as I do that, you see we have a bunch of droplets falling at randomly offset time periods. If I want to scale the amount of offset, right now it's just offsetting them from 0 to 1 second, or a random number that's 0 to 1. So if I multiply that by 4, now we have constantly falling droplets, or this is more of like a laser or something like that. Primnum, use primnum if you want the random number to be unique per primitive or per line. If I did point number here, you can see it's offsetting randomly every single point. So it depends on what you're trying to achieve. Sometimes you want a unique number, like here, primitive. I want to delete the primitive. For my bounce height, I want that to be a random number per point. But for this offset, or for this time offset, I want this to be a random number per primitive. Again, if I want to start moving these lines around, I could do that. Let's just make another float. This will be the X offset. And I'll set that, if I just set that equal to 5, Let's go down here and apply the offset. So just say at p plus equals set. We have the x offset and then 0 for the other coordinates. So this is moving it horizontally over 5 units. If I do a random number per primitive, then our droplets are getting offset or moved, translated over randomly. The random number is unique per primitive. That's why we're doing primnum here. If I do it again, ptnum, this is just a situation where I don't want a random number unique to each point of the line or each like individual particle that's making up our droplets. We want it just to be for the whole parent line that it belongs to. So again, just takes a bit of practice, but there's situations where you want to use your random numbers to be unique per primitive, per point, per vertice, or anything like that. So this random offset right now is this number gets generated. It's between 0 and 1. If you want to, you could subtract 0.5 from that. So now my x offset is scaling things both positive and negative. So the 0.5 will center our random number at 0. So half of them are like 0.5 or positive numbers and half of them are negative numbers. We probably want to do the same thing for z. So we can do float z, offset. Yeah, I mean, quite literally, it's, if we just go back to our single line and you visualize these numbers, these are the point numbers. So the random number, or it's like a random dice roll for each unique number here. And then if I visualize the primitive number, you can see it's just one unique number that belongs to all of these lines. So when you run it in a wrangle, primitive number is saying, give me the number of the primitive that I belong to, or the parent primitive that the point is a member of. So it's a little bit weird compared to other programming languages and stuff like that. It's like the way that the code runs over the geometry. So our z offset, again, we'll do a random, can just reuse this and put it into z. But you can see there's an issue is that these droplets are only getting offset diagonally. We want unique like 3D or 2D positions because we're just offsetting 2 dimensions, x and z. And that's just happening because these random results right now are giving you the same numbers. So if I do just offset that, then you can see my droplets here are fully random. Otherwise, I'm sliding or I'm offsetting x and z by the same random number. And then because those are synced up, it's not giving you a full like 3D or full spatial distribution. So can offset this one here just to be safe. You could keep giving things different. If you don't like the result, you could just offset this, and then you'll have random time offsets for your droplets. If you want to be even more optimized, you don't have to do that, but if you want to, you could say like, if time exceeds 3 seconds, delete the point. So earlier we were removing the primitive, the line that the point belongs to have it simulate the splash. And then we're saying here, after the time exceeds 3 seconds, the splash is done. We could remove the point just to be a little bit more kind of optimized. Visually, it doesn't look that different because we're already fading things out. But if I'm not doing a color manipulation. If you're doing like a scene, maybe your background is the light background. Then removing the points here is a little bit more efficient, or it's just a little bit helps you achieve the result for what you're trying to do. So certain situations you could either just fade it to black, or just to keep expanding on ways that you could achieve this. Just different options that you have is remove point instead of setting the color to black. So I'm going to go back to my dark background. And with these X and Z offsets, if we want to art direct that, you can multiply them by numbers to scale the distribution or the range. So for example, my X offset, if I multiply that by 10, then I know that my droplets, my rain is going to fall anywhere from like -5 to +5. No worries. It's not. I'm not offended by any joke or bad joke or anything whatsoever. I'm slightly ignoring the chat because I'm just trying to blow through these steps. This gets recorded on YouTube and stuff like that, so I'm not trying to do a ton of banter right now. So I'm sorry if it feels like I'm ignoring you. So it's not an issue. So we're spreading things out, X offset, multiply it to stretch it out by 10, a factor of 10. So instead of being -0.5 to +0.5, we're stretching it out to be -5 to +5. That's pretty cool. Trying to think here, doing like some art directing of this. We're pretty close to the end result. You might want to change maybe like the rate. I think that they were like bouncing, the gravity of the bounce was a little bit weird. It was like they were pulling down quicker than they should have been after they exploded or burst. A lot of this stuff is up to you. This is like your bounce height. Maybe so we adjusted the rate of expansion. If we do another multiplication here, this is going to be like the total distance that the droplets expand. So this will say scale splash radius. And then this is our map to radial directions. So it's feeling pretty comfortable, hopefully. Let me just keep going in. This is going to be random offset per drop. And by drop, I mean primitive. So this is a time offset. And then this is just our looping of time. And this intersection direction and speed, you have control over it. Set the X to different directions, and you have rain that's falling. Maybe like there's wind, you want more gravity, or faster, more intense gravity, or something like that, you can scale the y direction. And then here, if you change your point numbers, you can change how many points the droplets or the lines are composed of. And with this total number of lines, this will be like the number of droplets, or how much rain, how much of a downpour it is. So you could even go pretty crazy with this stuff, and it still will run pretty quickly. So Vex, all this stuff happening in here, like I was saying, is multi-threaded, or will run in parallel over each point is processed simultaneously on different threads of your processor. Yes, very, very procedural, very cool. So if you want rain that's falling from higher, you can change that pretty quickly. A lot of these parameters you can control pretty easily, and it's pretty responsive. So even with like the Z offset, could do expand that out. Maybe we want this to be like 40 units or something like that, and then you're closer to even like filling a whole environment or a whole scene or something like that, and maybe do more points. Maybe this maximum scale of the bounce height, do this. This is going to be like 12.5%. Yeah. So that's the rain system. The offsets, I use the slider. Yeah, if you want to set this up, you can do it using sliders. Then you can put them in the viewport and visualize them. If you're submitting stuff to a supervisor or things like that, that can be helpful. So I don't know what, maybe just like this splash radius. I could just do the CHF for channel float. Maybe this is going to be, I already have comments, so I'm already like a step ahead. This will just be splash radius, and CHF is for a float, like a single value. For this, that's 3 values. This is the vector. So if you do CHV, then that's saying the channel is going to be a vector channel, or 3 components. So this will be just like rain direction. So the reason to use this syntax is it's shorthand. With Wrangles, it's nice is that you get sliders that will automatically be created for them. So do this, go back to our horizontal. This was maybe 12 or something like that. So now you're a little bit more controllable. Definitely, like if you're making something reusable, having these parameters is nice. You can also drag them over into the viewport, and then you get the sliders like that. So we have different direction sliders here. I think you have to go into the clicker mode to move them around. So that's nice. And then if you're submitting things to a supervisor or to the client or something like that, you make a flipbook, it will have these sliders, then they could see like the values, or if you're just making notes for yourself, it becomes more useful too, or whatever. Make Vex function interact with the custom ground plane. That would just be on the scope for today's example. This is more of just a demo for assuming you have a flat ground. There's definitely ways to handle uneven ground or things like that. At a certain point, this is a good homework assignment. At a certain point, this kind of fully procedural method will break. Like if I have a character running through the rain, getting stuff to like string and drop down his body, you might want to go with the actual proper simulation and then like Eventually you might want to do like surface tension or a proper flip simulation, but depends on your situation. If this is just for an environment that you need rain going around the camera, or you want mist, it's quick, easy to set up, so it fits that situation well. And then these are just like kind of demos or learning examples. So none of these are really intended to be like fully used for production. Is more of just like a learning step. You want to create a result that's pretty cool or interesting or whatever. So that's the idea behind it. All right, so we'll do one more share of the file. This will be